Okay, hey everyone. This is the last problem that we finished up in class today. And remember, if we're trying to find the solutions, meaning the x and y equations relative to t, with t as our variable, for coupled differential equations, we first need to find the eigenvalues, their associated eigenvectors, and then substitute them into our nifty little formula, that we have written up at the top of the screen here. If we are given initial conditions, then we can find the a and the b values by simply solving a system of equations for when t equals 0. We'll find the a and the b values, and I showed you how to do a little check, because when you do these exercises, you may not get the same solution as is written in the back of the book, because we can use a variety of eigenvectors. Right? Because we have a rule and we could substitute any numbers into these. The question is the relationship between the variables. Are those relationships consistent? And that's essentially what we're looking for in terms of checking our solutions. So let's take a look at an associated concept. Oh, the screen kills me. All right, I'll use the keyboard. Phase portraits. All right, phase, not face portraits. We're not looking at this, we're looking at a graph. Now a phase portrait shows how two variables change over time. So phases obviously mean different periods of time. So essentially what we're doing is we're saying, how do x and y change as time goes on, as time increases? So let's take a look at example 2. Now in example 2, the example 2, we did this problem, 1A1. We were given this. And the only thing that's really important is the eigenvalues and the eigenvectors in order for us to draw our phase portrait. So we had a lambda 1 of 4, a lambda 2 of negative 3. The associated eigenvector we chose was 1, 1. And we could have, come up with a number of eigenvectors. And the other eigenvector that we used was 2, negative 5. Now, what we're going to do is set up an xy axis. All right, and first thing, let's draw the vector for the eigenvector associated with lambda 1. So let's draw P1. All right, that's 1, 1. All right, so that looks generally like this. All right, and since this eigenvector is greater than 0, eigenvalue, is greater than 0, that means these values are moving away from the origin. All right, so I'm just going to put those arrows on there like that. Now let's draw the other eigenvector. Let me erase that scribble I just wrote up there. All right, so 2, negative 5, and just draw it approximately. Doesn't have to be perfect. I guess it would look kind of like this. And now, since this eigenvalue is less than 0, these values are going towards the origin. All right, so this is associated, this is P2. Let me jot that down. That's P2. The other one is P1. They're associated with their special eigenvalues. Remember, the eigenvalues that are positive, their arrows are pointing away from the origin. The ones that are negative, the arrows are pointing towards the origin. So now, what we're basically doing is we're saying for every, what is the combination, what is the pattern of xy points? And here is what it is. We're simply going to follow these arrows. When we have one positive and one negative eigenvalue, all we have to do is follow these arrows. Look, it said down and right. down, and right in that section. How about in this section? Well, it's easy. We just follow these arrows. It's going to start this way and turn that way. All points in this section, they're going to go that way. Just keep up that pattern. And then it's super easy to follow. So this is a general phase portrait for this differential equation. We're showing how the x and y variables change over time. Now let's take a look at some general rules around phase portraits. All right, the equilibrium point we're going to assume is 0, 0. All right, so it's basically when both of these variables equal 0. All right, and so when we have two real eigenvectors, I want you to notice this image down here on the left. All points will be, two real positive eigenvalues. So this one right here, this vector here is associated with, hang on, let me change my color here. This one is associated, one second, I'm sorry. This vector is associated with lambda 1, which was a positive value. Where's the other vector? This vector is associated with lambda 2, which is another positive value. So remember, those arrows are pointing away from the origin whenever we have a positive eigenvalue. Now, what happens? What arrows do we need to follow? What general direction are our, I guess, pattern lines going to go? The points move away from the origin towards the vector of the larger eigenvalue. So we are going to be approaching, we're going to be going this way. So, hang on. All right, so if we look at all the points we can draw, they are going to start along the vectors. They're going to all start from the origin, right? And it starts along, following along the eigenvector associated with the smaller eigenvalue. So we can see this is going here, and then it eventually goes towards the larger eigenvalue. Remember, this was our larger eigenvalue right here. All right, and so if we want to look in this other area here, once again, we're going to start along the vector associated with the smaller eigenvalue, and then it's eventually going to start following the larger eigenvector, well, the eigenvector associated with the larger value. Again, and for this space, this region up here, starting at the origin, we're going to follow along the eigenvector associated with the smaller eigenvalue, and then we're going to follow that direction of the eigenvector associated with the greater value, and then same here, starting along eigenvector of the smaller eigenvalue and eventually going the same direction as the eigenvector of the greater value. And this is considered an unstable equilibrium point. I think you can see why. Now, if we have two real negative eigenvalues, we can see a similar pattern, but since negative eigenvalues move towards the origin, well, what do? Let me jot down what these, let me color code what these original vectors are. We have this vector, 1, negative 3, so that's this guy. Since the eigenvalue is a negative 3, again, arrows pointing towards the origin. The other one is negative 2. That vector is 0, 1. Okay, so this is the vector associated with that eigenvalue. And they are pointing toward, all points will move towards the origin and towards the more negative eigenvalue. All right, so they start out parallel to the more negative eigenvalue and then move towards the origin. Oh, I'm sorry, towards the not more negative, the greater eigenvalue. I'm sorry about that. All right, notice I should have done that in green. So yeah, it starts this way and it's going towards the origin, remember. And this one starts with the in the same direction as the lesser eigenvalue, and then it goes towards the greater eigenvalue. And this is considered a stable equilibrium point, all right, because they're all merging towards that point 0, 0. Saddle is like the phase portrait that we just did, where you have one positive and one negative eigenvalue. And remember, what we're going to do is simply first draw our vectors. Whoops, I picked the wrong color. Sorry. Here we go. Which one is 5, 2? This one's 5, 2. Am I right? Yeah. This one is 5, 2, associated with a positive eigenvalue, so moving away from the origin. And this one is 0, 1, associated with a negative eigenvalue, so moving towards the origin. And these ones are the easiest to do, where you have one positive and one negative, simply because all we have to do, like we did in the other example, is follow the arrows. Look, in this region, where are the arrows telling us? It's saying go down and then go right. Boop. Here, we're going to follow the arrow. Down and left. Doop. So on and so forth. Just follow the arrows. And this is called a saddle point. Equilibrium point. So let's practice that. Go to the next slide. I'm going to pause here and ask you, based on what we just did there, for you to pause and match each of these phase portraits with the associated solution to the system of coupled differential equations. All right, and I want you to notice that we can identify the lambda based on the two different lambdas based on the exponents for each of these solutions. All right, so go ahead and pause and see if you can do that, and then I will come back and show you what I was thinking. Okay, so what I did was I found my eigenvalues for each of these based on, sorry, pick a color, based on the coefficient of the t variable, all right? And so take a look, A and C both have a positive and a negative eigenvalue, so those are both considered saddle point equilibrium points. So let's see, they're not necessarily all going to go towards the origin, they're going to go in different directions. For A, I take a look at these vectors and they fall on the axes. And so I notice what's going to happen. It's got to be this one right here. All right, so we're going to start at the lesser lambda value. So we're going to start with on the y-axis, and then go towards the x-axis. Oh wait, no. It actually doesn't matter. We just have to follow the arrow, follow the directions. Okay, I'm going to stop talking about that one. I think you know why A is B. So let me put a little B. There we go, right there. For choice C, again, we're looking at another saddle point, so where the arrows will sort of be following in the general directions. It's not going to be stable or unstable. And let's just identify the vectors. Where do we see a vector of 3, 2, and 1, negative 1? That looks like this one right here. And notice how all of these are following the pattern of arrows that we see on the green lines. So C is C. Now the other two are going to be super easy to identify. Why? Because one has two negative eigenvalues. And remember, when we have two negative eigenvalues, all points are going to go towards the center. Boom, right here, D. And then system D, we have two positive eigenvalues. That is going to be an unstable equilibrium point. And so, going away from the origin, yeah, that's going to be graph A. Phase portrait A. All right, and so that's that. I want you to know that I am not going to test you on making a phase portrait, but I may, on this weekend's exit ticket, ask you to do a match like we just did here. Not exactly the same, but similar. So using those clues that you have, understanding that when you have two negative eigenvalues, all points are going to go towards the origin, positive eigenvalues are going to go away from the origin, and it's unstable, so on and so forth. All right, so I hope you can complete exercise 12F. Obviously, in problem number 1, it's going to ask you to draw some phase portraits. Give it your best shot, and send me an email if you have any questions. Okay, I'll see you on Wednesday.